It's great to be here. I have several of my students and postdocs working here, and I'm very proud of them. But this is a fantastic meeting. It really bring about the people who contributed the lion's share of work over the years in chemistry. Okay, this is a marvelous meeting, and I hope that I will not disappoint you. I love surfaces. Everything I do, for whatever reason, is related to surfaces. What I'm going to tell you, but what I'm working on are not surfaces, but they are interfaces. And virtually every phenomena I studied ends up to interface more than a surface in more ways than one. Now, let me just figure it out how to do this. I will talk about surfaces that are very important in our life. And I chose three: molecular catalysis science, and this is my major contribution. Then the information storage, integrated circuitry, which is a $3 trillion technology we all live with, and including my laptop is taking advantage of this. And then a newer energy conversion technology, which is the lithium-ion battery. And one of your people here, Jonathan Horowitz, worked in my laboratory for 3 years, and he knows more about this than certainly I do. Now, the major avenue for the last 30 years is nanoscience. You go to catalysis and you find that the enzymes, homogeneous catalysts, heterogeneous catalysis, are all nanoparticles. Look at the size, 4 nanometers for trypsin. This is the best catalyst for making polypropylene, titanium catalyst here. And this is a heterogeneous catalysis, a bimetallic one. They are all nanoparticles. Now, in the last, I would say, 30 years, nanoscience allowed us to go to the molecular level with the instrumentation that were developed to understand on a molecular scale how catalysis occurs. Now, catalysts are made as nanoparticles, metal nanoparticles, on mesoporous oxide synthesis, on mesoporous oxide surfaces. This is how they are usually made. Usually you make it with colloid chemistry, and the colloid chemistry nucleates and grows nanoparticles where you can stop the size at some point. And let me, I am not sure, yes, sorry about that. So at some point, and you can make nanoparticles of any size you wish, but of course, up to 15 nanometer, we call as nanoparticle. And you can change the shape, the nanoparticle various ways. You change the size, and then you do chemistry with it. Now you do chemistry on a support. The support is usually a silica support, which is mesoporous. You put a transition metal salt on top of it, you bake it, and then you take sodium hydroxide and leach out the underlying silica, and you get this mesoporous oxide transition metal right there, and then you put nanoparticles into this material, and in a way that the nanoparticles either go in this catalyst or stay out. If the pores are small, the nanoparticles, let's say platinum is 3 nanometers, it cannot go to the micropores, so it stays outside. And this sort of catalyst called bifunctional because the oxide does chemistry, the metal does chemistry also, and this is the name. Now, if the mesopore is large, what you find that the smaller, like the 3 nanometer platinum, can go inside the pore, and this is called a single-site catalyst because the chemistry occurs at the oxide metal interface. Now, let's go to the next technology. The technology here is the integrated circuitry. This was when I joined IBM in 1960, the transistor was everything. And the transistor basically was a single crystal or a nanoparticle. And then a small company formed out of Fairchild, which is called Intel. And the Intel had 3 people in the beginning, Moore, Noyce, and Hungarian Andy Grove. And the 3 people started to make integrated circuits by combining the transistors into a bigger and bigger integrated process device. And so the device right now is around 10 nanometer transistor size. And so to show you what's happening here, it's the device is now, this is a 7th generation integrated circuitry. If you look at the sizes, this is 20 billion transistors, 20 billion transistors. And the transistor, according to Moore's law, the number of transistors changes according to this law, and there is a roadmap of making an integrated circuit ever larger transistor sizes, and as a result, your computer can do much, much more with the number of transistors that is increasing according to Moore's law. Now, the density of these transistors are right now is about 10 nanometers, and it follows this roadmap. It looks like this. It's a fantastic device, but in order to do nothing but electron transport, it heats up, and you have to put a coating on it which allows to stay at a uniform temperature, which is usually hafnium oxide or titanium nitride, something like that. So it's a passive coating which also prevents the defects moving in the transistors such that it works for decades, basically without decomposition or deterioration. So the next technology is much newer. This is the lithium battery technology. My son has a car which works on lithium batteries, the Tesla, and it's a fantastic car, and he goes to San Francisco from his home, about 20 miles outside, and when he goes home, he plugs in the car, and within 2 hours, it recharges, and he's ready to go again. But that 2 hours is not like filling your car with gasoline, and so this technology has to be improved in order to fill up in 30 minutes or less. This is a technology, it's a constant change. Now it works with a silicon or graphite anode, and then the lithium is intercalated in the silicon. It goes into this electrolyte, which turns, because of polymerization, turns into a solid, and then it goes through the liquid to the cathode, and it deposits there. If you want to recharge, then you break the cathode bonds, and the lithium is diffusing into the silicon back, and you are ready to go again. Now, it looks like this, and it's a very good catalyst, but it has a finite lifetime because the lithium intercalates both in the anode and the cathode, and as it intercalates, it destroys it. So this has a finite lifetime. But it turns out that if you fluorinate the electrolyte, organic electrolyte, which is this one here, then it lines up, and it repels the lithium ions, and the lithium ion increases the speed of transition from the anode to the cathode by 2 orders of magnitude. So this is a technology in development, and if you talk to Jonathan Horowitz, he's in Tel Aviv, and he will tell you more than you want to know. Now, I think the future is going to biointerfaces. Our body is a biointerface, and the biomaterials, each one is a unique one. The human brain, I mean, we have a polymer coating our skin. Underneath you have water, and then there are either solids like hydroxyapatite, or the brain is swimming in spine fluid, and this is important enough not to be left to the medical doctors. It's clearly that biomaterial science is the future of this interface sciences, and I'd like to call it to your attention. Now, let's go to molecular catalysis. How catalysts work. The atomic level characterization is possible by technologies related from the synchrotron. From the synchrotron, many of these synchrotron techniques can give you the vibrational spectrum, the composition, the size, and the scanning microscopy basically gives you the mobility of the species on the surface, and this actually, on an atomic scale, you can use under reaction conditions to see what's happening while the catalysis is running. Now, the technique that was Berkeley developed was the some frequency generation vibrational spectroscopy that is surface sensitive, because this omega 1 plus omega 2, some frequency at 2 different frequencies, is forbidden in the centrosymmetric environment. And so the surface is not centrosymmetric, and so it gives you a surface technology to determine what's happening on the surface under reaction condition. Here is an ethylene hydrogenation reaction, and what you see are 3 peaks, and these 3 peaks are showing the this is not working. No, it's not working. That's all right. It shows the vibrational spectrum, the spectra of what you see, the various species. Thank you. That worked. Okay. Okay, thank you. Okay. And so this is cyclohexene hydrogenation, dehydrogenation, the species on the surface, and this is how we get the mechanism of reactions that are taking place. Now, the X-ray photoelectron spectroscopy can be used now at up to 10 torr, and it gives you composition analysis on the surface, and lately the graphene coating is very important to study what's on the surface, and it can show through liquids or high pressure gases which are existing on the other side of the graphene membrane. The surface composition shows nanoparticles, and in these nanoparticles, the size, let's say a bimetallic, platinum, palladium, rhodium bimetallic. In nitrogen oxide, the rhodium segregates to the surface, and in carbon monoxide reducing conditions, the palladium segregates to the surface. So in a bimetallic, the surface segregation changes the chemistry that occurs, and this one can be studied in various bimetallic materials, and so we can see that the metal nanoparticles, if it's bimetallic, changes the surface composition and its catalytic chemistry as a result. Now, the scanning tunneling microscope shows mobility on the surface. If you do a reaction like cyclohexene dehydrogenation to benzene, or hydrogenation to cyclohexane, and you look at the surface, you see absolutely nothing. Why? Because these organic molecules are moving on the surface, and what you see, the movement is about 100 angstrom per millisecond, and so as it moves, it gives you no picture. However, if you poison the surface with carbon monoxide, you see the mobility stops, and there is no chemistry. As a result, the chemistry stopped here, and all you see is the poison surface. Not only that, but the surface itself is restructuring under the influence of carbon monoxide or another gas, and you can see the steps on the surface meandering and developing in a different structure. Once you remove the gas, then the structure goes back to its structure, which is a step structure in the surface, and so the surface is in fact constantly restructuring, and this dynamics is at the heart of catalysis. Now, the finding, which is very important, is that the size and shape of the nanoparticles control the catalytic reaction rates and the selectivities. Now, we have studied many reactions. These are rather simple reactions, but they are very easy to identify what it does. For example, here the furan is the furan is hydrogenated to dihydrofuran and then to a linear molecule. So all these molecules undergo changes that we can follow as a function of size of the nanoparticles. And so you see the size of the nanoparticles here, and you start with furfural, which is this molecule. If you increase the change of platinum nanoparticle size, the furfural increases in concentration to furfuryl alcohol, and the furan that forms from furfural goes down as a function of nanoparticles. And here is a very important technique to study the Fischer-Tropsch reaction, carbon monoxide hydrogenation, and you find that as you increase the particle size of cobalt, it increases by 5-fold. And if you look at the product distribution, it also changes as a function of size, like this here, and the products change, and the nature of products goes to a much higher molecular weight hydrocarbons as a function of size as well. Now, here is a situation where you have a molecule which is this is metal cyclopentane, and it breaks a CC bond here and there, and it forms these isomers. And depending on the shape of the nanoparticle, the isomer changes. Okay. Now, this is covalent bond catalysis, because the metal exchanges electrons with the adsorbed molecule, and this is covalent bonding. But there is another type of catalysis, and this is what we call acid-base catalysis, and this one is interestingly depending on the oxide support. If you look at the oxide support for a reaction like protonaldehyde, 2 double bonds forming this molecule, if you put it on silica as a support, you make very little molecules, and these are the compositions. If you increase the titanium, you put in a support of titanium oxide, you get much higher turnover rate and very different compositions. So the oxide metal interface does what we call acid-base catalysis. And this was the discovery of hot electron flow between the oxide and the metal, and this at the oxide metal interface is where the chemistry occurs. And so what you do is, if you shine light on a metal, then you excite the free electrons in the metal, and they have a mean free path roughly of about 10 nanometers or so. And during that free mean path, if you take the metal surface and you put in an oxide here, what you find is the mean free path. What you find is the platinum electrons go through the 10 nanometer interface here, and they form a flow of charges from the metal to the oxide, and then when that happens, there is a chemicurrent, we call it chemicurrent, and it is the white, and the turnover rate is correlated with the chemicurrent. So the current and the chemistry that occurs at the interface is combined. Now, we have a theory, Martin had Gordon in our chemistry department, and he looked at the transition state of how in this reaction, which is CO oxidation, happens, and there is a CO2 minus forms, which is the transition state, and in fact, it's sorry about that. And this ends up with a 3 electron. This is from the chemicurrent and CO2 formation. If you look at the water formation, hydrogen-oxygen reaction, again, the chemicurrent forms, and what you are getting is H2O minus as a transition state, and so this is what would be an acid-base catalysis, because the molecule is ionized at the interface. And so this is another very important catalytic reaction path, which are at the oxide metal interface. And so this is the heart of making high-octane gasoline. If you take N-hexane, and in this case, and in this case, the form, I apologize. You make the CC bond breaking, and that relates to forming the isomers of high octane with the platinum titanium oxide or niobium oxide interface, and if you use the oxide alone, you don't get much except decomposition. If you use the platinum alone, it's not as good as the oxide metal interface. Now, there are very interesting situations when you look at the cobalt oxide platinum interface, because you get CO oxidation rate 7,000-fold more than when you take any other platinum, other oxide interfaces, and I can explain it to you. It's a very interesting chemistry. Now, now comes the discovery mode of how to combine the 3 fields of catalysis: enzyme, heterogeneous, and homogeneous. What we found is that if you use a catalyst, in this case it's palladium, and you change the size, you go to about 2 nanometer in size, the reaction is CO oxidation. There is an enormous 30-fold increase in the CO2 formation. If you look at the catalyst, you find that it's not rhodium metal anymore, but rhodium 3+. It's an oxidized rhodium, and below 2 nanometers, this oxidized rhodium is much higher turnover rate than the metal. In fact, this is what happens with all the transition metals. If you take platinum, when you go to 1.1 nanometer, 1.5 nanometer, you have basically all platinum in this case. But if you go below, then the platinum becomes 2+ and 4+, and the ratio of oxidized platinum to metallic platinum is 13:1. And so that gives a totally different product distribution. Now, Jens Norskov, who looked at this closely, found it by taking gold does again form a high oxidation state when he goes to small nanoparticles, if you take a gold nanoparticle, a big one, and this is the size of this nanoparticle, the red part is where the oxidized gold forms. By the time you go to about 55 nanometers, and you should remember that 1 nanometer is roughly 40 atoms, you go to that one, the whole gold nanoparticles becomes gold 2 plus and 4 plus. And so when you go to these small nanoparticles, then the oxidation state changes. Now, this got us into heterogenizing homogeneous catalysis. We took a support like this dendromer support, which is sort of like a branch of a tree, and you can put platinum or any metal on it and any size, but the high oxidation metals are the small ones. Then you put it into a support, like a silica support, and run the reactions. What you find is that you can get homogeneous catalytic reactions, and we have 13 papers to show that we can take the 40 atom palladium, platinum, gold, and other transition metals to carry out homogeneous catalytic reactions. Now, here are the rhodium catalyzed homogeneous catalytic reactions. Now, so I have a colleague, Dean Tost, who is a homogeneous catalytic man, and we do these studies together, and so we can heterogenize homogeneous catalysis this way. Now, this is just to show how we do that. We put the nanoparticles into the dendromer support, and do it that way by putting it into a mesoporous medium also. Now, what is interesting, now this is a paper we published about 2 months ago, 17 reactions we found in the literature that have been done by all 3 fields of catalysis. This was done by homogeneous catalysis, heterogeneous, and enzyme, the same products. This is bizarre because that means that the people who do these 17 reactions never talk to each other, but they did it in all 3 methodology. And so the question is now, if you can do that, can you heterogenize enzyme catalysis, and somehow you may get different products by hybridizing the 3 types of catalysis. And so we are doing here, and we are now doing the enzyme heterogeneous interface, and let me show you how we do that. And so there are many types of enzyme reactions, and I have a colleague who is an enzyme chemical person, and we do the work together, and he teaches us how to do enzymes and heterogenize them. You can take here is an aldolase enzyme, and this is a reaction, and if you put this, the product comes through in water. These work in water as NADH to go to NADH plus, and that gives us a turnover rate of this enzyme if we heterogenize it. So what we do is you take a strand of a DNA and put it on a surface, which you can put a glue on it. The glue is an aniline glue on a quartz surface, and when you do that, you can take the enzyme and put on the other strand of the DNA, and when you put the enzyme on the surface, you form the double helix here, and you have it anchored onto the surface. Now, when you do this reaction in the water solution, you get this turnover rate measured by NADH formation, and you get 50% when it's anchored to the surface. And it stays on the surface without leaching for many, many turnovers. So it appears that we can heterogenize enzymes, and then this is the SFG spectrum, the vibrational spectrum of the single strand, the double strand, the double strand DNA, and we are in the way to get the vibrational spectrum of the enzyme as well. Now, this is what we are doing. You can go for unifying all fields of catalysis. And my hope is that we find, if you develop the hybrids, different type of products in this case. And so finally, we can integrate the three fields of catalysis. Now, this is where we are, and I really recommend you, if you are interested in catalysis, try to go through this integration because it may give us a totally different picture of how catalytic reactions occur in an integrated mode with the three areas of enzymes put together. And so this is the surface science approach of molecular catalysis to integrate all three fields. I am hoping that it will work. If you are interested in how we do these things, there is a PNAS article, Proceedings of the National Academy of Sciences, to put it in perspective there. I really think that this is an important and interesting direction to go in the future. Now, it's the biointerface is equally important to go to study the interfaces. What I'd like to leave you with is that we have not studying surfaces, we are studying interfaces. And virtually everything that we do on surfaces, including catalysis, integrated transistor technologies, and the lithium battery interface methodology is all interfaces. So we have to go to the molecular level to study all these technologies because they are interfaces of some complexity, but they are all available for study and development. Thank you very much.
Well, thank you very much indeed, Gabor, for this beautiful survey. I think we have time for a couple of questions and comments, if there are any. Perhaps may I ask a question with regard to the lithium battery? Is the amount of lithium high enough to provide the world with lithium when each car is running on a lithium battery? Would it not be better to use sodium batteries?
Apparently, there are certain countries, Bolivia, one of them, okay, which is no problem with lithium availability. And so I don't know the answer. It depends on whether you can replenish the lithium and not, don't throw away a car.
There was a question over there, yeah. Is there a microphone? Or speak up, perhaps.
just a matter of terminology. Surface is a kind of interface, right? Also, surface is an interface between a gas or a vacuum and a solid or a liquid. But my question is regarding the bimetallic catalyst. I think it was palladium, rhodium.
Palladium, yeah.
Yeah.
One of them.
Yeah. Does the gas-induced segregation of one of the elements, I don't remember which one, maybe palladium, affect catalysis, and how? The segregation itself, does it affect the catalytic properties?
Good question. The segregation is of the order of a few seconds. If you have a 16 nanometer nanoparticle, okay, the segregation means moving a couple of layers under reaction conditions. And so this time scale is much faster than the following restructured surface gives you the product distribution that you want. Okay. Now, if that would be slow, okay, then you would have a major problem there. And in many cases, if you have a reducing gas or an oxidizing gas, and you change the composition, you can play with the product distribution as you change the composition of the gas. And this has been done. This has been done. It is clear that the definition of the surface structure is possible because we have XF data from the synchrotron to follow the change along with the gas composition change.